Welcome to our discussion on ratios. We've only got one objective today, and that's to write and interpret ratios. And a ratio is simply just a fraction, right? So we've got a bunch of different ways of talking about fractions. We talk about them as rates, ratios, proportions, percentages. They're all just variations on a theme. So a ratio is just a fraction that's used to compare two measured quantities. And in this case, the units are the same, right? When we were talking about rates, the units didn't have to be the same. Sometimes ratios can be written with English, 1 to 2. Sometimes they have a little colon in between it, but that's still read as 1 to 2. And then sometimes they're written as a fraction. Not usually. They're usually written in one of these first two forms. Usually the middle one is the most common, by the way, in case you cared. Simple examples, right? If they tell us that certain enrollment was 321 women to 214 men. If we want to write that ratio of men to women, then we have to put the number for men first, right? Men to women. If we were doing women to men, we would just switch places and have 321 to 214. And then you could write it all three ways. Now, with ratios, one of the rules is you always want to reduce them. So you would never say the ratio was 2 to 10. Instead, you would say it was 1 to 5, that kind of thing. Now, with these numbers, you're not sure if they reduce until you do some work, because it's not real obvious just by looking at it if these two numbers have anything in common. I mean, obviously this one's even and this one's odd, so you can't divide them both by 2, but they might be both divisible by 3 or 7 or something along those lines. So you always want to reduce your ratios when you can. You reduce them to whole numbers. You don't ever reduce them to fractions, or sorry, decimals. Now, like I said, those previous numbers were both reducible, but by a very odd number, something that was very hard to see, 107, and so it reduces down to 2/3. Now you would have seen that if you had just taken the original fraction and thrown it into your calculator. If you don't own a fancy graphing calculator, there are free emulators all over the place. You can get Wabbit EMU off the internet and then download a ROM file for it to get it to work. And then you can do fancy things like this, where you take your fraction, gives you a decimal, then you do math and change it back into a fraction, and it reduces it for you, 2/3. Equivalent ratios are exactly what they sound like. They just express the same, which is what we saw in the previous example, where all of those ratios were equivalent because they all reduced back down to the same 2 to 3 ratio. And that's what you always want to do, is reduce them down to their lowest equivalent ratio. Try this skills check, see if you can reduce it down and write the ratio of women to men in lowest term. And of course, 6 to 4 both reduce by 2 and give you 3 to 2. Here's another simple example. 40 adults in America include 15 women, right? In the 40 under 40, write the ratio of women on the list to the total number of adults on the list. So we're not going to do women to men, we're just going to go women to total, and then for part B, we're going to do women to men. So the number one thing that's going to get you getting these things wrong is not paying attention to the details of the question. So for part A, it was 15 to 40, and of course 15 to 40 would reduce, and we would say 3 to 8, or 3 out of every 8 adults on the list are women. That's why we would leave it to the total, so it gives us an idea of how many out of the total. And then, of course, if we went the other way and figured out, well, if there are 15 women, subtract that from 40, that gives us 25 are men. And now we're doing the ratio of women to men, or 15 to 25, which reduces to 3 to 5. Now, if you remember what the previous example was, it was 3 out of 8, or 3 to 8, and this is 3 to 5. Well, it makes sense, because if it was 3 out of 8, then that means out of 8, 3 of them were women, and the other 5 had to be men. So we could have got this answer straight from this and said it was 3 to 5. That's the beauty of ratios. Okay, how do we interpret some of these? One such example is trying to point out that farm-raised tilapia might not be the healthiest fish to eat. A study in an online health journal claimed that when they looked at the bad, right, omega-6 fatty acids and compared them to the good omega-3 fatty acids. In farm-raised tilapia, that ratio was 11 to 1. So you're basically getting 11 bad acids for every one good acid. And that right off the bat doesn't sound great. But you're not really sure if it's bad until you compare it to other, wild caught fish that we know to be healthy. And so here are other types of fish. Salmon we know is one of the better ones for getting the good omega-3s. And this table lists the omega-6, the bad ones, and the omega-3, the good ones. And so we could compare it to the 11 to 1 that we were getting out of tilapia. I remember 11 to 1 was 6 to 3, so it was already set up in the right direction as far as this was first and this was second. So if we take those numbers and put them straight into ratios, we can compare them, right? 11 to 1 versus all of these. And right off the bat, you can see that 11 to 1 means this number was bigger. These all have the second number bigger. So we already know that they're better and quite a bit better. If we turn them all into unit ratios so we can actually, compare apples to apples, so to speak, we see that instead of 11 to 1, we get these decimal ratios, really small amounts to 1. So tilapia is bad according to this article, and it's really, really bad according to this article because the differences are really quite large. How about another example using maps? Ratios and scaling are versions of being able to use maps, right? Every map will have a scale on it where it'll tell you a certain distance on the map will equal a certain distance in the real world, and it's usually inches to miles. In this case, it's 1 inch equals 5 miles. You could have one where 1 inch equals 1 mile, or you could have something where 1 inch equals 1,000 miles. It just depends on the map and how much area they're trying to show on each page. So now that you know the scale, you can figure things out when you want to find, let's say, the distance on the map between point A and point B measures 3 inches. Now, I don't know if that's a straight line. I think it's 3 inches along the red path. And then you want to know what's the actual distance in real life. Or if you want to take an 11-mile walk one day in this area, you could find 2 points on the map that are a certain distance away that equals 11 miles. So let's try both. First one is simple because we already know 1 inch equals 5 miles. So if the distance on the map is 3 inches, don't we just take 5 and multiply it by 3? Yeah, simple. We get 15. But the actual math involved, in case it wasn't something as simple as 3, let's say it was, 2.7 miles. Well, then what are we doing? Well, we're still basically multiplying that distance by 5 because that's the ratio. 1 inch equals 5 miles, so however many inches we have, 2.7 of them, we multiply them by 5. That's the beauty of having a unit scale, and most maps will always have a unit scale. They're not going to be cruel and say 3 inches equals 7 miles. You're like, oh crap, now I got to deal with that fraction, right? It's always going to be 1 inch equals something. Now, part B is only marginally more difficult because we're solving backwards. And when we solve backwards, we no longer have a unit measure because now 5 is on the bottom, right? So we no longer have that 1 on the bottom to make the math easy. But it's still pretty simple because to get rid of fractions, we multiply by the fraction. So we multiply both sides by 11 to get rid of it. And then we multiply both sides by 5 to get rid of that one. And then we're left with 11 equals 5x. We, of course, want to solve for x, so we divide both sides by 5, and then we get 2.2. So we need to find something on the map that's basically 2.2 inches long, and that will give us an 11-mile walk. Let's say you have an older map or a well-loved map, and unfortunately the guide has been ripped off of it, and you don't know what the scale is. But you do know that the distance from Chicago to Albany, New York is exactly 816 miles. And on the map, you can measure that distance, and it's 1.4 inches. Well, now that you know those two things, you can actually figure out the ratio of your map so that you can find distances to other things. Like if you wanted to figure out the distance from Chicago to St. Louis, Missouri, and on the map it was 0.5 inches, you can use this first ratio of 1.4 inches equals 816 miles and be able to solve for how long is a half of an inch in miles. So we set up our ratio of 816 miles per 1.4 inches is equal to our unknown x miles per zero point 0.5 inches. Now, could you have set it up the other way? Could you have done 1.4 inches per 816 miles equals zero point 0.5 inches over x miles and get the same answer? Absolutely 100% the answer is yes. It would not have mattered at all. But, however, it's always easier mathematically, and you'll have less chance for making mistakes if you put the unknown in the top of your fraction. So it's always better to have x in the top of the fraction rather than the bottom of the fraction as far as the work is concerned. It just makes it easier and there's less opportunity to make mistakes, but absolutely both ways would give you the exact same answer. So if we have it set up this way, we can see that again, like we always do, we multiply by the bottoms of fractions. So we multiply both sides by 1.4, and then we multiply both sides by 0.5 to get rid of both fractions. When we do that, we get 408 equals 1.4x. Then, of course, we divide by both sides by 1.4, and we have x equals a little over 291 miles. And that's the beauty of having x on top. When x was on the if x was on the bottom, you'd have to multiply both sides by x instead of by numbers. And it's really not any more difficult. It's just where students tend to make more mistakes. So to save yourself the headache of possibly making errors, always set up the initial problem with your variable on the top. And if you're ever presented with a question on a test or homework or anything where it's set up the other way, just flip it, right? If this ratio is the same, then if you flipped it, 1.4 over 816 is going to equal 0.5 over x. So if that's the ratio they gave you, just flip it before you even start and start from this one instead. Okay, our last example is going to use multiple ratios. So instead of just one number to another, we can have multiple numbers, in this case 3, but we can have 4, 5, 6, 7, 100 numbers in a ratio. It doesn't matter, it can work. The math gets ugly, but you're probably not going to see any more than 3 at a time. So a certain ratio of cashews, almonds, and Brazil nuts in some sort of, raw nut mix, trail mix of some sort, says 2 to 3 to 5 in every bag. And that means for every 2 cashews, there are 3 almonds and 5 Brazil nuts. Or most likely it's ounces, right? They're not number of nuts. So for every 2 ounces of cashews, you get 3 ounces of almonds and 5 ounces of Brazil nuts. Okay, now suppose that there are 5 ounces of cashews, the first one, in a bag. How many ounces of the rest do we have? Now there are a couple different ways to solve this. I'm going to show you the way that most textbooks do it, and then I'm going to show you a better way. All right, so most textbooks are going to make you do these types of questions in 2 parts. They're first going to say, all right, well, take one portion of the ratio. Just take the one that we're dealing with, right? They told us we have cashews, so we have to start with cashews because that's the only one we know. We know there's 5 ounces of cashews. And then just pick one of the others. Pick the next one because it just seems logical to go from left to right. And then we got cashews and almonds. Cashews and almonds are in a 2 to 3 ratio, right? 2 to 3. And so now, based on that, we know that the ratio of 2 to 3 has to hold where we actually have 5 ounces of that first nut. But already, I don't like this because what did they do? They broke our own rule of putting x in the denominator. Well, like I said, flip it. Turn this into 3 halves equals x over 5. Multiply both sides by 5, right? 15 over 2 equals x. And then multiply both sides by 2. 15 equals 2x. No, why would you do that? You've already got x by itself, right? So your answer is 15 halves, which is 7.5, right? Don't just become kind of a mindless drone always doing the same steps over and over again. When you multiply by 5, x is all by itself, and that's the nice thing about putting x on top. So we now know there's 7.5 ounces of almonds, right? And here's their work where they had x on the bottom, and it takes a little bit more. They still get the same answer, but it takes a second step because you didn't flip it. So technically flipping it was that one step, so it all works out in the end. But you get the idea. I think it's easier to put x on top. All right, then we repeat the process with the 2 to 5 ratio for Brazil nuts and get 12.5 for Brazil nuts. And we go, okay, there's our ratio, 5 to 7.5 to 12.5. Technically, you would never, ever, 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 ever list ratios with decimals. It just gets ugly and confusing. Um, but for this example, you would, right, because they wanted to know the precise amounts, but you would always take that ratio and you would reduce it to whole numbers and you would get it back to 2 to 3 to 5. Now, the second way I was telling you that I think is easier is you find that multiplier, because a ratio is really like a bunch of fractions. And when they tell you you have this ratio of 2 to 3 to 5, we know right off the bat that if we multiplied everything by 2 and got 4 to 6 to 10, isn't that the same ratio, right? You can multiply them all by 10 and get 20 to 30 to 50, right? And everything's the same. So really what you can think about is if you start with your original ratio of 2 to 3 to 5, and then they tell you you have 5 ounces of this, then what's your multiplier? What's your x? What did you have to multiply 2 by to get 5? So you can think of 2 times something equals 5, or x equals 5 halves, right? Or x equals 2.5. So there's your multiplier. Now if you multiply everything by 2.5, you're going to get the new ratio. So 3 times 2.5 gives you 7.5, right? And 5 times 2.5 gives you 12.5. I think that's a lot simpler than doing two things with those fractions. It's up to you guys. If you don't like it, if that confuses you, just go back to the fraction example. Okay, our last example, same type of thing. Only now instead of telling us how much of one item they have, they tell us how much of all of the items we have. So we have a bunch of bags of bags of different types of nails, long, medium, and short, and they're in a certain ratio of 4 to 5 to 6. That means for every 4 long nails, you have 5 medium and 6 short. And if a bag contains 300 total nails and they want to know how much you have of each, well, you could, again, set up your ratios and go from there. But I like the idea of thinking about multipliers. Because if we start with our original ratio of, 4 to 5 to 6, we know that that would give us a total of 15 nails, right? 4 plus 5 plus 6 is just 15. But we don't have 15 nails. We have 300. So what's the multiplier? Well, set it up the same way we did before. 15 times this x has to equal 300. X equals 300 divided by 15, which equals 20. 20 is our multiplier. Multiply everything by 20. We get 80, 100, and 120. Double check it. Add those together. That's 300 total nails. Much easier than the way the book's going to show you with setting up all these fractions and then solving each individual ratio with the fractions. No, no, no. Just do the multipliers and get the exact same answer that they got. Okay, so that's my tip for ratios: is use the multiplier trick if you can. If you understand it, hopefully you do.